derivative of, let's say, f of x equal to x to the okay. Simple. Let's start with something simple. Here, in this example, let's say that I want to find the derivative of x to the cube. What would be the derivative? 3x squared. Okay, so the derivative of that? 3x squared. Okay, so in this case, for example, what did I do? For this, which is the original function, the basic function, to get to this into the derivative, the process is called what? Differentiation. Okay, that's what we did last semester. Now, imagine, if this is my derivative, and I want to obtain the original function, we're going to go into the inverse process, which in this case is going to be called anti-differentiation. So in this case, for example, x to the cube is a function, the derivative is 3x squared. If 3x squared is my function, the antiderivative, well, only an antiderivative is going to be x to the cube. Do you understand that? Okay. Now, imagine, for example, that I have another function. Let's call it g of x. But the function is x to the cube plus 2. Or another one. Let's say h of x is x to the cube minus 7. If I want to find the derivative for those two, the derivative for this one is going to be what? 3x squared. The derivative for this one is going to be 3x squared. So what happens here? For all of these functions, or any function that has this shape plus or minus a constant, the derivative is going to be the same. Why? The derivative of the constant is equal to 0. So that means that this is only an antiderivative for this one, an antiderivative for this one, an antiderivative for this one. But if I want to find the general antiderivative for this function, I need to generalize the answer. So how to do that? Well, in this particular case, we're going to call it, I don't know, let's say capital F, to represent any function, an antiderivative. The general antiderivative for f of x 3x squared. Well, let me change the letter. Let's put a and this. If this is the function, the antiderivative, the general antiderivative is going to be what? Think of this from here to here. The antiderivative for this is going to be x to the cube plus c. Plus c. This plus c represents any constant that I can add here. It could be plus 2, minus 7, plus 1 million, it doesn't matter. So this one, for example, this is going to be the general antiderivative. Okay, of what? Of this function. So, from here to here, I differentiate. From here to here, I anti-differentiate to obtain the general antiderivative. Is that clear? Yeah. This plus c has a special name. It's going to be called a constant of integration. And it represents a family of functions.
Pero ¿cómo puedes saber, o sea, por ejemplo, si la función fuera nada más de que x al cubo, o sea, ¿cómo puedes, o sea, a fuerza solamente tendrías que poner más c?
If you integrate that, yes, they will proceed. But don't worry. On Friday, we have a new topic which is called particular antiderivatives. In that case, you need to use initial conditions. If you have initial conditions, special conditions, then you can see which value has to be in there. But you need to have more information. But in general, the antiderivative for this is going to be x to the cube plus c. In general. Okay? Is that clear? Yes. Okay. Another example. Let's say that I have a function is equal to sine of x. This is my function. But I don't want to find the derivative. No, I want to find the antiderivative. Okay? So, the question will be, find the general antiderivative of this one. What will be the answer? How do you think of that? Okay, think of which function, what will be the function whose derivative is sine of x? Cosine or minus cosine? Minus cosine. Okay, so the antiderivative, to represent that, we're going to use a capital. To distinguish from that, we're going to use capital F of x. The antiderivative is going to be minus cosine of x plus c. Plus c. Okay? How do you know that this is true? Well, if I find the derivative of this, the answer has to be that. Okay? So remember, if the question is general antiderivative, remember to put the plus c at the end and look for the function whose derivative is the one that you have, which in this case is this. Yes. Later we're going to see special conditions, more information to get that. But right now, just like that. Questions? Yeah.
Se pone la mayúscula para diferenciar que es una antiderivativa.
It's just a way to represent it. It doesn't really matter. The letter doesn't matter that much. But it's a way to generalize that. It's not the same function, but it's related to that. That's why we're going to use this one. Same as this one. If I decide to call this one I to the x, to maintain the relationship, we use a capital I. Okay? Questions so far? Okay, this is just the introduction. Now the important part is this. In here, for example, I did this mentally, right? But there is an operation for that. There is notation for this. So for that, we're going to see the process of the indefinite integration. Okay. In this case, I did this mentally, but I need to put notation to represent that. If you remember, in derivatives, we use the prime to represent that. But in here, in calculus 2, we're going to use the integration notation, the integration symbols for that. But let me explain how to get it. To understand this, remember this notation from Math 5, dy over dx equal to f prime of x? Yes? What does that mean? Derivative of y with respect to x equal to the derivative of the function. This is called the Leibniz notation. Remember? We use this when we use related rates of change, the implicit differentiation, all of that. Yeah? And also, you remember, I can separate this. If I put this to the other side, then you have dy equal to f prime of x times dx. Remember that?
Yes.
This was a differential of y equal to the derivative of the function and differential of x. Yeah, it's the last thing that we did last semester. Do you see that with your teachers? Ok. Un paréntesis. Esto lo vimos al final, cuando vimos, por ejemplo, lo de razones de cambio, cuando vimos lo de las gráficas al final, cuando vimos, por ejemplo, lo de implicit differentiation, lo de sobre dt, todo eso. ¿Recuerdan? ¿Mande? Aquí no me estoy despejando. Okay? Okay. So in this case, this is the differential. But the thing about this is that if I have a differential, I want to obtain the original function. So for that, what I'm going to do? The same notation, yeah. But what I want to do is cancel everything. I want to get to the original. I want to cancel the derivatives. So for that, I'm going to use this notation. This symbol here. This symbol here. This symbol is like an S, just a little longer, more stylized. This means the integration sign. This is the integration sign. This one is called the integration sign. And what this means is that using this notation, I can cancel. So the integral of dy, then it becomes the original. which in this case is y, equal to, well, the operation, which is this, integral of the derivative of the function, and the answer for that will be the original function plus c. And that's the process. It's the same as I did here, but adding the notation of the operation. Okay? We're going to do an example with the notation, okay? It means this symbol cancels the differential to obtain the original function. This symbol cancels the derivative to obtain the original function, plus the constant integration. Okay? Integration sign, the dx is important because it represents the variable of integration. And this part here, the derivative, yeah, but it's called the integrand. It's like radicand in radicals, but in this case it's called integrand. Very good. Questions? This is just the beginning. This is the introduction of everything. Okay? So you can understand why the different symbols represent. A little parenthesis here. Ustedes a lo mejor no entienden qué significa esa S como línea. En realidad esta S es como sigma. ¿Han visto lo que es la letra sigma? ¿Sí? La letra sigma, si ustedes recuerdan de mate 4, mate 3, no me acuerdo cuando lo vieron, significa una sumatoria de valores. Entonces realmente esa integración es como una sigma pero estilizada, porque en realidad una integral, no esta, sino la definida, que tiene que ver con valores, significa una sumatoria de valores. Se llama sumas de rima. Eso no lo vamos a ver aquí en clase, no nos da tiempo. Pero de ahí donde viene. Cuando vemos la definida, voy a volver a explicar esto para que entiendan de dónde viene el signo de integración. No vayan a examen, nada más como for your information. Okay. More examples. So the question here is, okay, how do I use that notation, the symbol of integral, to solve anything? Well, let's say that in the exam, the question is, solve the integrals. That's the question in the exam. And then it says, okay, integral of 3x squared times dx. That's the integral. Solve it. What do? The same thing as I did in the beginning. I'm going to find the antiderivative of this, which was x to the cube plus c. And that's it. And that's it. Okay? This is the operation, then you solve with the antiderivative. Okay? Be careful. When you write an integral, be careful that if you put this symbol, the variable is also important. Okay? If you, for any reason, put the integral, this, and you forget to put the dx or whatever it is, it's wrong. Pero ¿por qué está mal? Es que no es lo mismo. Por eso que les acabo de decir ahorita. Porque me está diciendo con respecto a qué variable va a ser. Si no les pusiera eso, no se podría hacer.
¿Hay como alguna fórmula para sacarla de...?
There are. We'll see that. Another example, and then we'll go to the formulas. Integral of, for example, that one. Integral of sine of x dx. What will be the answer? Minus cosine of x plus. Okay? Good. Let's go with the rules. You remember that in alpha you solve all the basic differentiation rules, right? So since this is the inverse process, there is also one for each, plus more. Okay, so in this case we're going to do the same thing as we did last semester. We're going to see each one of the integration rules and then 6 examples. Number 1. Let's say that I have the integral of just dx. No function here. Well, there's a function. Okay. It's implicit here. What would be the integral for that? Just c? No, because if you have c as an answer, the derivative is 0. So this is not 0.
1.
X plus c.
X plus c. Why? Because here, even though there's nothing, there's something there. There's a 1. 1 times dx. This with this cancels, of course. So the integral of this is x. Because the derivative of this is 1. Okay? Second one. Integral of a constant. I'm going to put k as a constant. Times dx. Constant could be a number. 5, 3, pi, e, whatever. What will be the solution? No,
Sí.
the derivative.
The constant.
Sí, ¿no?
The constant x. Constant x plus c. Why? Simple.
Porque...
It's like a number, so
Yeah.
it's like 1x.
Example. Integral of 5 dx. The answer is 5x plus c. Why? Because the derivative of 5x plus c is 5. Okay? Number 3. One of the most important ones. Integral of x to the n dx. Now for this one. Remember that last semester when you found the derivative of x to the n, that was the power rule, right? What was the derivative of x to the n? The derivative, remember? Exactly. So in this case, it's the inverse process. Instead of multiplying times n and subtracting one exponent, now you're going to divide now. So x to the n plus 1 over n plus 1 plus c. That's the integral. Why? Okay, one example. Integral of x to the cube, well, x to the 5 dx. If I were to follow that rule, what's my integral? X to that plus 6 over 5 plus 1, 6 plus c. Okay, let's prove it. Is the derivative of this one?
Yes.
X to the 6 plus 6 over 6 plus c. Derivative is derivative of c, 0. Derivative of this one, 6x to the 5 over 6 equal to the 5. Is that the same? Yes. That's true. Yeah? But this is the simple one. Let's do another one. What happens if I have this? Integral of the square root of x to the 5 dx. Do I apply the same rule? Remember in derivatives, what was the very first step in the derivatives before the rule? Simplify and rewrite. Can I rewrite?
Yes.
Okay, so integral of x to the 5 halves dx. I just rewrote equal to. Now the integral, can I apply that now?
Yes.
Yeah. So it's going to be x to the 7 halves over 7 halves plus c. Yes or no? I added 1 and then I divide by the same thing. Can I simplify or rewrite this one? Yes. 2 7 square root x to the 7 plus it. That's the answer. I rewrote, I solved, and rewrite again. Just like we did last semester. So expect something like this in the exam, something like we did last semester. Big integrals where you simplify until it's simple. Yeah.
Okay, no sé, o sea, no sé de qué igual que la.
What?
I don't know what happened from when you rewrote. No, when you rewrote the answer.
This? Sorry, right? What about this? It's a fraction in a fraction. What do you do with this? You the reciprocal. Remember the rule for the reciprocals. If you have, for example, 1 over a fraction, you can rewrite that into this. That's what it did. 7 halves in the denominator becomes 2 sevenths. It's a fraction. Okay? Good. Questions? Good. Exception. What happens if I have integral of x to the minus 1? Will it work the same way or the same way?
No.
What would be the answer? There's an answer. Okay, let's see. If I apply this, what do I have? Then you say, okay, then it will be x plus 0 over 0 plus c, right? Is that possible?
No.
Is that true? No. So what's the answer?
Minus 2.
No.
X.
Okay, I have you with this. X to the minus 1. Can you rewrite this somehow? Yeah. So integral of 1 over x dx. Question. Which is the function whose derivative is 1 over x? That's the answer. Ln of x. What do I put the little bar there? It's an absolute value. Why? To make sure that the argument is positive, so the logarithm exists. Yeah? Be careful, please. Be careful. If you have x to the minus 1, ln of x is the answer. Questions? Don't worry, we have 3 days to practice and see all of this. Today, tomorrow, Thursday, to practice with activity and everything, so we have plenty of time to understand. Good. More rules. This is more like a property. What happens if I have integral of a constant times function? Could be any function, whatever. What happened in math 5 in the derivatives when you had a constant times a function and you want to find the derivative? What do you do with the constant, with the coefficient?
Multiply.
Exactly. That coefficient goes outside. So that's a property. You can put the coefficient outside the integral. So coefficient times the integral or whatever times the dx. That's a property, more like a rule. And the other one, if you have integral of an addition or subtraction of functions,
Which part?
you can separate them. Integral of f of x dx plus minus the integral of g of x dx. Just like with the derivatives. Sample. of x plus 2 over x to the cube minus 7x to the 4th dx. Good. What's the first step? Separate and also rewrite. Yeah? So we can separate addition, subtraction, the coefficients out at the same time if you want to. So you have 5 integral of x to the 1/2 dx plus 2 integral of x to the minus 3 minus 7 integral of x to the 4 dx. Is that necessary? Not quite. Rewriting, yeah, but separating or put a constant out, not that important. That's only if you want. Okay, like a property. You can do it, fine. You don't do it, fine also. But you can visualize that better. About these questions in this case? No? Do you know how to do it? How do I write this and this? Yeah? Good. So, can I find the integral now? Yeah. 5 times integral of x to the 1/2, following the number 2, the number 3. X to that? 3 halves divided by 3 halves. Plus 2, solution, x to the minus 3.
1 over
X to the minus 2 over minus 2 minus 7 x to the is that it? Before that? Not all of them. Not all of them. Why? Because in this case, for example, you could put plus c, plus c, plus c, but at the end it's a constant of integration for all of them. So you can just summarize into a single plus c at the end. That's it. Okay? Fine. Questions? No. Now what? Now, yeah, we need to simplify and rewrite again if necessary. So, will be what? 5 times x to the 3 halves over 3 halves will be?
10 square root of x to the cube.
Over 3 minus
1 over x squared.
very good.
Minus 7 x to the power.
Plus c. That's my answer. Questions? Do you see what happened here? I rewrote everything, applied the rule, all of them, and then just rewrite and simplify. So, don't forget, please, don't forget that if you separate the integrals, you always need to put the variable dx, 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 and at the end, the plus c. Every time you have the symbol of integration, you put the variable here. If you forget to put this, then it's wrong. It's always corresponding. Sign, variable, sign, variable, sign, variable. Or don't separate. Doesn't matter. But at the end, put that. Questions? No? Sure? Too easy?
Sí, ¿no? Sí.
Sí, grabaste.
Sí, está grabando.
Ya todos están espantando.
Profe, un saludo pajarito.
A todos mis fans. Okay. More rules. Fine. The trigonometric rules. Sine of x, integral. Minus cosine. Very good. Cosine of x, integral. Positive or negative? Careful, huh? Careful. In Math 5, the derivative of cosine is negative sine. The derivative. The integral, no. Same thing here. The derivative of sine is normal cosine, positive. The integral is negative. Careful, because it's one of the things that most students get wrong, the sign. Come again, you're going to get it wrong. So, be careful. Just be careful. Secant square. Square now. Just 10. Cosecant square. Ah? Positive or negative? Negative. Secant x, tangent x, integral. Secant. Cosecant x, cotangent x, integral. Minus cosecant. Okay? The same thing, derivatives, integrals. E to the x integral? E to the x. The simplest one. Simplest one. E to the x, e to the x. Always. Always. Just be careful. If you have something like e to the true x or something like that, you need to apply something else. It's the chain rule in very well. But it's just e to the x, e to the x. Okay? So, those are the basic rules. Basic rules. But we're also going to see it's a little more complex one. For example, integral of secant of x, integral of cosecant, tangent, cotangent. Tangent, cotangent, okay. Now, for these ones, these rules, they don't come from simple derivatives. Okay, there's a little trick here than the other ones. For example, the first one, secant of x, is ln of secant of x plus tangent of x. The other one minus ln of cosecant of x plus cotangent of x. Then, what else am I missing? Ln of secant, ln of sine of x, a to the x over ln of a, and x ln of x minus x.
¿Profe, eso es de memoria o va a dar formulario?
The thing is that all of those rules have an explanation. They have a demonstration to get them. We'll see them, just not today. Because in this case, for example, this one, to get this one, to get this one, to get this one, this one, this one, and that one, they come from the inverse of the chain rule, which is called substitution. So all of this, right now, for this part, for these 2 weeks, for example, will be by memory. Voy a tratar de pedirle a ti, si por ejemplo se les va a meter en el quiz, pues darles formulario, porque yo prefiero demostrárselos. Sí, vamos a ver cómo se demuestra, nada más, no ahorita. Falta ver todo lo que es el inverso del chain rule, el inverso del product rule, que es un poquito más laborioso. Divertido, pero laborioso. Entonces, por ahorita sí van a ser como de memoria. Me faltan 3 más.
Ya me había emocionado.
One. For these 3, the same thing. You need to, there's a way to demonstrate them, but we need to use trigonometry. ¿Se acuerdan el semestre pasado, los que llevaron conmigo, que les sí demostramos cómo llegar a la inversa, las funciones trigonométricas inversas, cómo derivarla? Para demostrar la integral es algo similar, muy parecido. Sí lo vamos a ver, pero no ahorita. ¿Contigo lo vieron? ¿Cómo demostrarlas? Bueno, no importa. Lo haremos, pero con más tema. ¿Por qué? Porque no me gusta decirles como que de memoria estas, pues no. De hecho, en cuarto debían haber visto cómo sacar inversas, no los de previo nada más. ¿Alguien aquí? Tú llevaste conmigo, ¿te acuerdas? Sí, ¿te acuerdas que lo vimos? Con triángulos. Sí, o sea, cómo sacar de esta, cómo representarla en forma de triángulo con Pitágoras y llegar a esa. Igual lo demostré en quinto también, pero para que vean cómo se sacan esas. Pero ahorita no se preocupen, lo haremos con más calma después, más para que las tengan ahí. Okay. Fine. Questions? Questions about this? Okay. Let's try one last example and then we go. Okay? Not that complicated. Let's try it. Okay. One last example, and then tomorrow we're going to be working with activity the whole class. Okay? Oh, very simple, right? Yes, it is. What's the first step? Rewrite and simplify. Can I do it?
Yes.
How? No, that's not it. It's not that I want to. No, I need to. ln of x, ln of e to the x, sorry. Can you simplify that, or do I need to apply the rule directly? Yes, exactly. I can simplify. In this case, ln of e to the x becomes just x. Huh? Why? Remember the properties. You have log base a of a to the x. Those two are inverse to each other. You have x as an answer. Same situation with the ln and e. The same base e. Plus, can I simplify this, or do I need to what? What do I do? Aha, this is multiplying those two, so you can simplify that. X to the minus 2 times x to the fifth power is what?
X to the 3.
X to the cube plus x to the minus 2 times 2x is what?
2x minus 1.
2 over x, or 2 to the x to the minus 1. 2 times x to the minus 1. Okay, is that it? Are you missing something? Like that? Very good. Ya les digo, o sea, igual que contigo, esto es importante. No, bloquea gacho. Si no me ponen paréntesis, quiere decir que nada más el de está multiplicando 2x a la menos 1. No, todo. Hay que poner el paréntesis. Por favor. Okay, now it's simple, right? Integral. X to the square over 2 plus x to the 4 over 4 plus, you need the 2, x to the minus 1, derivative integral. Is that it? If you notice, in this case, I didn't divide each step.